Hi friends, in the previous lecture we have seen about the definition of group and what is the mean by the abelian group. Okay, now we have to discuss about the example of group. Okay, so obviously when we see the definition of a group to any set which forms with a binary operation which forms an algebraic structure, that algebraic structure is group if it satisfies certain properties. Okay, so these are the mainly four properties of closed property, associative property, existence of identity and existence of inverse. Okay, if these four properties are satisfied, that time we say that the given algebraic structures forms a group. Okay, if with this another one property, commutative property is also satisfied by that set or that algebraic structure, that we call as an abelian group or commutative group. Okay, so now we have to discuss about the examples to understand the definition of group or how the algebraic structures forms a group. Obviously in the previous lecture we have taken an example, or we say that the set of integers is also an algebraic with respect to addition and multiplication forms a group. But here we have taken particular example. Let us see. Show that the set of all positive rational numbers forms an abelian group under the composition defined by. Okay, under the composition defined by that A star B is equal to AB by 2. Obviously in this we have an operation star. Okay, obviously the operation is defined in such a way that the A into B upon 2. Okay, these are the two numbers A and B, and these all are the positive rational numbers, and we have to show that it is an abelian group. So obviously we have to show the five properties: closed property, associative property, commutative property, existence of identity and existence of inverse. Okay, let us see how. So let the Q denote the set of all positive rational numbers, that is Q plus. We defined an operation A star on Q plus as A star is equal to A into B by 2 for all AB belongs to set of positive rational numbers. Okay. So to show this algebraic structure Q star is a group, we will see about the first closed property. Says for all AB, if we take any two rational numbers or positive rational numbers and we define an operation A B by 2, and it should also belongs to the Q plus. Okay, let us see some example. If we take two positive rational numbers, let us take as 3 by 2 and one will be 5 by 3. Okay, these are the two A and B. Okay. So what is the composition we have? That A B by 2. Okay, this is the operation on, that is A star B is equal to AB by 2. So let us see how the closed property satisfies. Okay, this is 3 by 2 into 5 by 3 divided by 2 according to our composition AB by 2. Let us see. Is equal to this 3 5s are 15 and 3 2s are 6 upon 2 is equal to 15 by 12. And obviously this is also a positive rational number. So the closed property is satisfied. Okay. Let us see about the associative property. Next property. Associativity. Let A, B, C, these are the three numbers belongs to the set of positive rational numbers. Then A star B star C should be equal to A star B star C. Okay, obviously it should be the same. So A star B is what by definition or by our composition A B upon 2 star C. We have to take the composition of these two. Okay. So first element, that's we have A B by 2 star we have to see. Okay, so our composition, that is this is the first element, and what is the second element we have, that we have to multiply, that is A B. So obviously it stands for A total and C upon 2. Okay, here see that C upon 2. Now this will become, this will forms the A by 2. Obviously we can write it as an A by 2 into BC by 2. Okay, and this we can make a form of this, and this is what? This A star B star C. Okay, this LHS equal to RHS. So the associative property is also satisfied by it. Next, obviously that the question is that abelian group. We show that is the abelian group, so commutative property should also satisfy. So let us say commutative property. If we have any two positive rational numbers, then A star B by our composition AB upon 2 is equal to, we can replace it BA upon 2 and this is not B star A. So commutative property is also satisfied. Okay. Next, we have to think about the existence of identity. Okay, and we know by the definition existence of identity, there exists an element E such that if we make an composition with any element of that set, that E star. So obviously the algebraic operation, that the operation we have star defined by AB by 2, it should be equal to an original element. So we have to find there what is the identity element for this set. Okay, so let us, by E star A is equal to A. Both the we can prove it, but we will take one side. E star A by our composition EA upon 2 should be equal to, which implies that. And obviously we will transfer this A to this side, because here we have the multiplication between A and B, right? So we will transfer this, and which implies that E is equal to 2. Therefore, 2 is an identity element for our this set. Obviously, that if there existent identity, then we can go towards the existence of inverse. So, what is the definition of existence of inverse? This with composition A star A inverse should be equal to an identity element. Okay. So obviously our composition is AB upon 2 A star B. So then between this we have A into A inverse upon 2 should be equal to identity element. Identity element is 2. We show is that both the ways. Okay. Think one by one. So we'll transfer this side. So A into A inverse equal to 4. So therefore this A inverse is equal to 4 by A, and this 4 by A is the inverse for over this set. And thus all the properties, that is closed property, associative property, commutativity, existence of identity, existence of inverse holds. So this algebraic structure Q plus, that is set of positive rational numbers, and the stars forms an abelian group. Okay, this is the example about the group. In the next lecture we will see about what is the finite and infinite group, okay, and the order of